These are well established. So they're Archimedes-style rules, okay, that basically state that if I did have a balance or a lever, and I had a two mass at one distance, and I have a one mass at two distances on the other side, that this is a perfect equality, that these two objects essentially weigh the same according to this balancing fulcrum.
Yes, that's absolutely correct. Sorry, my throat is a bit sore today.
Okay, it's going to state that yes, those two things do equal each other, and I can oscillate it. That is, I could put energy into it, and it will oscillate back and forth with the one mass going twice the velocity, and with the two mass going one velocity.
So far, we are still in full agreement, Gary.
Perfect equality. Now, there is no equality in terms of their kinetic energy, and that's the problem with their theory. That's the nonsense they're preaching. And their argument is the real equality is 1.4, the velocity, will equal a two mass with one velocity. Now, that doesn't happen. It doesn't balance. It doesn't work. And it doesn't have anything to do with being reasonable and rational.
And of course, at this point, time and time again, you fail to understand this. Time to explain what happens in a lever regarding kinetic energy and why the 1.4 thing, as you call it, keeps popping up.
Okay, back with a more serious voice. So let's say you have a rigid lever, fulcrum in the middle, with a two mass at a distance r on one side, a one mass at a distance 2r on the other side. This system is perfectly balanced in terms of torque. The heavier two mass is closer, the lighter one mass is farther, so it doesn't tip. It's in rotational equilibrium. Now you let it swing freely, maybe after lifting and releasing it slightly. As it begins to rotate, the one mass moves along a bigger circle, the two mass moves along a smaller circle, but they both complete each rotation in the same time. So, one mass moves faster, twice as fast linearly. Two mass moves slower, half as fast linearly. Now, where does the kinetic energy go? The answer is geometry plus rotation speed. The lever is rigid, so it forces a certain speed ratio, in this case 2:1. But when the whole system swings, the total kinetic energy is shared among all rotating parts based on their speeds and distances. The parts farther from the pivot get more energy because their speed is higher, and energy grows fast with speed. In order to understand this more deeply, we need to bring up the moment of inertia again and angular energy. I know you think this is baby talk nonsense, but right now I don't give a damn fuck about that. Moment of inertia is a real damn thing, proven over and over again. Now here is the explanation, whether you like it or not. What is moment of inertia? Intuitively, think of it as the rotational equivalent of mass. Just like heavier things are harder to push in a straight line, objects with more moment of inertia are harder to spin. But here's the twist. Moment of inertia depends not just on mass, it depends a lot on how far that mass is from the axis. So, a heavy object close to the pivot equals small moment of inertia. A light object far from the pivot equals surprisingly large moment of inertia. Why? Because mass far from the center contributes much more rotational resistance. Not linearly, but quadratically. How does this relate to energy? Now imagine you want to spin a lever. The total rotational energy you give it depends on how much moment of inertia the system has, how fast it's spinning, angular speed. The more inertia it has, the more energy is needed to spin it at a given rate. And here's where it all comes together. Parts of the lever that are farther from the pivot contribute a lot more to the total energy, even if they're lighter. That's why your one mass at twice the distance gets more kinetic energy than the two mass. It's farther out, so it moves faster because of the rigid lever. It contributes more to the system's moment of inertia. It gets a bigger share of the total energy. Even though the torques balance, the energies don't. So even if the kinetic energies are unequal, the lever can still be perfectly balanced. Why? Because balance, in the physical, mechanical sense, is about torque, not energy. Torque is the force times the distance from the pivot. So a light mass far away can balance a heavy mass close by. This is independent of how much kinetic energy each mass has when the lever swings. When the lever starts to move, let's say you slightly lift one side and let the lever rotate. The lever stays rigid. Each mass moves in a circular arc around the fulcrum. Because of the geometry, the farther out mass moves faster. So the forces are still in balance, equal and opposite torques, but the kinetic energies are different because of the different speeds. This feels weird at first. It's tempting to think, if one side has more energy, shouldn't it tip or overpower the other? But no, that's not how rotational motion works. Think of it this way. Balance is about how hard each side tries to turn the lever, torque. Energy is about how much motion each side contains once it's already turning. They're related, but not the same thing. So in summary, yes, the lever can be balanced in torque, even if the energies are unequal, because torque and energy are not the same thing. Let me once again try to explain this even more clearly. Why this doesn't break the balance. You might now think, wait, if one side has more energy, shouldn't it pull harder or tip the lever? But no, because balance or tipping is about torque, not energy. The lever is already moving, and it moves as a single connected piece. The distribution of energy just tells us where the motion is more intense, not who is winning.
Alright, enough of a video. I'll keep the 1.4 thing for another video. I hope you enjoyed the amount of frustration this video has given you. It will only get better and better. Till next time, and such.